Uh, Thanks for having me here. My name is Nate Booth. I'm a developer advocate for the OpenSearch project and an ambassador for the OpenSearch Software Foundation. Uh, I'd like to talk to you a little bit about vector search, semantic search, and various other related things. But we all have to stop and think about what we're seeing in the news cycle today about AI and all of these like things. It's got the media in a chokehold. Employees being laid off because AI is now generating text as good as our documentation people and all of that kind of stuff. It's got people thinking that this semantic search part of AI is this super complicated, super intimidating kind of thing. And my goal here today is to show you that it's not that complicated. The generic concepts that you need to understand semantic search are very simple. You'll leave here today feeling pretty comfortable with it, like most of the things. So I'll share a little bit about that, some of the concepts involved, and I would not be doing my job if I did not talk to you about OpenSearch at least a little bit. So I promise this is not a sales pitch. I won't make it sound like a sales pitch if I can help. Anyways, so we'll learn what vectors embeddings are. We'll learn what the relationship is between vectors, embeddings, and the language models that everyone's talking about. How to store your vectors in OpenSearch, and then how to query them. It's pretty much the basic. Those are the four things you need to know about how to implement semantic search. Don't feel like an imposter. These concepts are grasping. So is everyone ready? I'm ready to move forward. Oh, that's me. That's enough about that. So like I said, I would not be doing my job justice if I didn't talk about OpenSearch at least a little bit. So I'm going to do that. It's a trusted, vendor-neutral open source platform for AI-powered search, analytics, observability, and vector database solutions. It's built with speed in mind, flexibility, and it really is a platform of choice for people hoping to develop large-scale applications that make use of AI and vector storage. Was that too sales pitchy, or should I skip that next time? Okay, awesome, thank you. Oh, search title. Okay. So that's here's the million-dollar question, everybody. Just what are vectors, or as they're often referred to, embeddings? What are they? Well, it's actually a pretty simple answer. Embeddings are the numerical representation of data. So the simplest form is this: is if you pass text into a language model, you get back what might seem familiar to a lot of these people. There is just an array of floating point values. So you pass in text. This language model does its calculations and crunching on this thing. And then what you get back is what you see on the right. It's just an array of floating point values. You see 3 of them there. But the output of that is a vector, just one of these things. So what do those vectors represent? And why are they important? So if you pass a couple of sentences to a computer and say compare these things, you can't really compare sentences. You can't it's not like it's math. You can't look at 2 sentences and say one is bigger than the other, or one is more of one thing than another. And so this is what language models do. They look at properties of a sentence. And so these language models have been trained to look at the positions of the words in a sentence, their relationship to the other words in a sentence, where certain words appear in sentences, whether a sentence is angry, whether it's boastful, false, all of these things. So for the purposes of my demo today, I've picked a language model that analyzes 768 different things about a particular token of text. So to think about that real quick, do you think if I wrote a sentence on a whiteboard around here that you could come up with 768 different characteristics of a sentence and then compare those to other sentences? All of the data that AI uses, all of the sentences that it works on, all of the semantic search is all done with numbers. All of the data that it works with has to be numeric. And that's why language models are very important to create embeddings. That's why embeddings are important. Because these language models can't work on anything but numbers. So that's the first input. Some models out there, some of these new fancy ones, analyze billions of parameters about any particular chunk. And so that's why they call them large language models. They are not. Some of them are manageable, and you can compare them with others, but they're not common. So I think I may have answered this already, but what do vectors allow you to do? Well, they allow you to compare and contrast data that's not numeric by a computer. So I'm sure you've all heard the media chokehold on RAG and AI and all this stuff as well. RAG makes use of vectors too. So if you want to have a retrieval augmented generation, so to ask natural language questions about your own data, the data is usually represented with vectors. RAG solutions will query a vector database to find their context to answer your question. So AI and RAG and chatbots would not be the same today, would not be the same without vectors. So what usually these vector databases, I'm going to step over here so I can point at stuff. Actually, I'll do it. One of these buttons. All right, so I hope the graphic isn't too small, but when we say, oh, we're doing a vector search, what are we actually doing? What we're doing is we are comparing the distance between two vectors. So you may have heard the physics definition of a vector where it's a direction and a velocity. So it's a direction and a distance. So these vectors are actually quite similar. So when these large language models, they try to characterize things, they use, imagines, just for simplicity's sake here, let's imagine a X and Y plane, like in algebra or geometry. Things that are similar in semantic definition get grouped in similar places. So just for this example here, we've got Wild West and Broncos kind of grouped similarly in this kind of graph here. So the language model stores those close to each other because it knows they're semantically similar. These are both things that you might associate with a rodeo, so it's aware of that association. They're things that you might associate with Texas, for lack of a better stereotype. Animals and things like that. So it takes these concepts that it's been trained to understand and groups them close to each other in this vector space. So what we're looking at here is just 2 dimensions of vector space. We've got X and Y, but for these large language models, they're trying to compare the location of a vector in in my case, the 768 dimensions. Or for the case of these larger language models, there's a geometric vector space that takes up millions or billions of dimensions. And so you end up with these vectors that are grouped together based on their semantic meaning in vector space. So if I were to do a search for something, let's say I did a search for a horse, or let's say saddles or something. Would that get stored closer to basketball or soccer, or closer to Wild West and Broncos? But probably closer to Wild West and Broncos. So we get the idea. They are semantically similar. The language model knows that, so it spits out a vector that puts them in the same approximate location. That is, in essence, a vector search. It's not so much a search as it is a comparison of distance. So when we see things like KNN or ANN, have you guys heard those terms before? That the nearest neighbor search is a classic. I just call it magic math. I'm not smart enough to do any of that stuff, but these nearest neighbor algorithms require a fair amount of compute. But what we're talking about is the nearest neighbors. If we have a query from a user that says, let's look for badminton. A neural search or a vector search is going to take that query, badminton, and then run that through the same language model. So we'll end up with badminton being represented by coordinates in geographic space. Whichever documents are stored close to that one are likely to be semantically relevant because they've been analyzed by the same language model. They've been given a vector based on the same calculations, based on the same criteria, and now they get stored in this dimensional space according to their semantic meaning. So we take a query, we get the embedding for that, we compare it to the embeddings that are in our OpenSearch database or your vector database, and whichever ones are closest, those are the approximate nearest neighbors. And so for ANN, that's approximate nearest neighbors. KNN is, K is just a number. If you want the 50 nearest neighbors to a particular vector, K would be 50. There's, if you'd like to know more about the magic math that happens when doing vector calculations, these distance metrics will also take someone smarter than me. The Euclidean distance, cosine similarity, but like I get it's been a while since trigonometry, but like the distance and angle between Wild West and Broncos, it can you take that angle and you calculate the cosine of that angle, and it kind of shows you how far they spread based on their distance. And that's what they mean by a cosine similarity. That's about as much as I know about any of those, but there's different ways to perform these calculations. There's different ways to build these graphs. A lot of companies have to kind of determine the trade-offs over recall versus precision. And that's always an ongoing thing for companies hoping to implement semantic search. There's this trade-off between compute capability or the compute necessity and how accurate you want your results to be. One of the cool things we can do with these two concepts, though, is if you've heard the concept hybrid search, we can, if we combine vector search with a plain keyword search, we get something that's called hybrid search, where we can search for semantically similar things as well as exact word matches. And so that, if you're running, say, an e-commerce site and you want people to get exact matches on their search, but then things that are semantically similar, like if I search for blue boots, I will likely get semantically related things: shoes, sneakers, boots, cowboy boots, whatever. But a keyword search would also return things that have blue in it. So we would get blue umbrellas and blue shirts, blue everything else. So combining those two for certain situations is actually advantageous, especially for an e-commerce site. Let's just pick one at random, Amazon. And if you do a search for something that you might want to buy, the worst thing that you can do is return no results. So you want to return some results to help someone find what they're looking for. So you'd probably want to combine search methodologies to get results no matter what was typed in, because that's better than zero results. Savvy? Is that everyone still with me? So I went through the process of building it. I made a quick vector workflow demo that I'm hoping to share with everyone here, but we're gonna build one of these. We've got a bunch of jokes, and these are all components of an OpenSearch cluster. These are all various features and capabilities that we use to build these kinds of workflows. So this is specific to OpenSearch, but I think that you'll find it in general similar. The first thing that you have to do when you're implementing semantic search is, well, you need a language model. And these models that create the vectors or the embeddings are called transformer models. So this is an example of the call that we would have to make to OpenSearch. And so we would register a model. This one is a sentence transformer, MS Marco, Distilbert based, TASB. I don't know what that means. But in OpenSearch, when you register a model, it returns a task. And so you use the task API to look up whether that registration is completed or not. Usually have to try a few times before it finishes, but once it does, you get, you get the magic model ID, which I think is what's showing right here. You get a model ID, and that's how you refer to it in OpenSearch so that it knows what model. So we've got a model, we've got it registered, one more API call to deploy it, and then you've got a language model deployed into OpenSearch just waiting to be queried for embeddings. And that graphic there is the part that we just built of our little workflow. OpenSearch uses pipelines as well. So when you're ingesting data, you don't have to take the data exactly as it arrived. What we have is called a text pipeline or a pre-processing pipeline. So this is the mechanism that we use to generate embeddings from the model. What we do is we're creating this ingest pipeline here. I'm calling it joke ingest pipeline because my data source is a bunch of dumb jokes. Anyways, we tell it to use a text embedding processor using this model ID, which should be the same one before. And this field map is the important part. What it's saying is this data is going to come in with a field named joke. And what I want you to store the embeddings in is a field called joke embeddings. So you're just saying, expect this data. Here's the actual data. I want you to embed that as a vector in this different field. And that's what we call a pipeline. There's lots of other things you can do with a pipeline, probably a talk for some. And so we create an index. The magic here is setting the KNN to true, so it knows to build the data structure in a particular way, and associate it with the pipeline that I just made. And then the last piece of magic here is this joke embedding field is going to be created by my pipeline. I have to tell it that it's a KNN vector field, and the dimensionality is 768. I've always found this a little troublesome because I shouldn't have to do a bunch of research on the model to know how many dimensions it uses. I feel like it should just be something that it knows. It should be able to figure that out. But anyways, you have to know the dimensionality of your language model beforehand and set up your index to make appropriate use of that. Then I think that creates the index, this call. Yeah, here's the dad joke index part of it. And then the cool part is where you actually put jokes into the database. Now I had to write a bit of code to do that, but after 100,000 entries, it goes through them one at a time. It sees that joke field, runs it through the language model, which creates the embeddings, and then stuffs those into the appropriate field defined in our text processing pipeline. Clear as mud? I'm going to check again. And so that's the part that we've made right there. We're putting these dumb jokes in my, and then the other important part is querying. I described this briefly before, but what we do is we use what's called a neural query. And I know it's semantic search, but we call it a neural query. And basically what that means is we're giving it a query text and then the model ID of the language model that we have to query. That language model embeds the query text so that it has a token. Remember that vector is a point in geographic space. And so you end up with the vector of the query, and then you plot it on that graph and you say, all right, which other ones are nearby? Which ones are semantically closest to this particular vector? And so it does that in real time when you query it, makes the embedding, compares them, and then returns the results. And that's what we refer to as a neural query. Of course, I've specified the number for K. I want the 100 nearest neighbors to it. And that's hopefully I'm going to make the cardinal sin of doing a live demo for you here today. We'll see how that goes. Is that cool? Do we want to see that demo? I am going to. I wrote a little bit of JavaScript. Well, AI wrote me a little bit of JavaScript. And so what I've done is create a little node express.js server that has a text search bar. When you hit enter on that, it makes that neural query via JavaScript and then inserts the results, giving it a similarity score and a joke ID. So let me see if I can. All right, so awesome. So what I'd like to demonstrate is that we're going to give this dad joke neural search app a topic. And what we're going to take note of specifically is that we're going to receive results back that did not contain the word we searched for, but they are semantically relevant. So let's try animals. And so some of these are pretty awful, but most of these are about animals. I'm trying to think of something that might have semantic relationships. So like fruit. I have a feeling we're going to get, oh, well, not a poop joke is what I was hoping. Where do fruits go on vacation? Paris. And so what we do end up with is, what kind of fruit do ghosts like? Blueberries. Cute. But what we end up getting here is the actual content of the joke, a similarity score, and then a joke ID. I was doing that just as a debug to make sure I wasn't getting the same joke returned from the query. But yeah, what I do have for you all is I took my little semantic search demo, made a GitHub repo out of it. So if you'd like to look at the JavaScript, all of the operations that were done on the OpenSearch cluster are in there, written using the JavaScript node.js package for OpenSearch. Uploads a model, registers model, deploys a model, uploads a bunch of crappy dad jokes. I will disclaim that I did not sanitize it. I take no credit for the bundle of dad jokes. Some of them were a little PG-13, so let's try to be adults about that whole thing. But if you care to look at my work and maybe contribute or try to build something just randomly fun, I would love to work with anyone who wanted to team up on something just to be arbitrarily creative. That was a lot. Can I answer any questions for anyone? Can I go back over something? two. I didn't see which one you went first, so. Yusuf. Go ahead, yeah.
So, like, maybe starting from so like an LLM is being used for generating the embedding.
That's correct, yeah.
Yeah. So, how are normal LLM models and embedding models different?
That's a good question. The question is, how are embedding models and LLM models different? My understanding is that these embedding models, or they're also called transformer models because they transform data into vectors. They're meant for that purpose. They're meant to follow their own internal programming to take that semantic meaning and give it numbers. Whereas like a chat AI, a chat language model, or something that was an agentic AI of some kind, would be taught to generate full sentences of text, and it would take its training data and generate something that was similar to what it had been trained with. So what you have to understand is that when they say language models are understanding English and they're generating all of this text, they're generating something that is computationally similar to what it has been trained with. You'll never get true like understanding of a subject. It's just working with numbers. And so the embedding models, they generate the numbers and that's it. Whereas these large language models meant to chat, they usually have a context, a chat history, a data source to draw upon when it needs to look up a new answer, things like that. So these models that I'm using here, they're only using them to generate embeddings. Did you still have a question over there?
Yes, so I was curious, like at what, kind of piggybacking off of that question, at what level does the complexity of a query begin to break down in terms of how it's parsed? Like if you have a more logic-oriented query, for lack of a better word, like would Boolean logic end up as part of that dimensionality?
I wouldn't think so. All of these models, when they're being built and compiled, they're all given what they call weights. And from what I understand, that means is how closely related various terms are in the sentence. Whether something has many synonyms, because if you do a search for bar, you end up with results that are also synonyms or misspellings. So you end up with a little bit of that. But I don't think there's a point at which it breaks down, because one way or another, that LLM is going to create a vector out of your data. Now, whether that vector is close to anything or not is another question. And that's actually a good point, because if let's say you've got a document way over here in vector space, but then the only document close to it is way over here, you're still going to get that result that's way over here because it's the closest neighbor to it. So you might end up with invalid results, but you still will get results in embeddings. Right there.
So, kind of like the embedding models, you see it with transformer models?
Yeah, the question is, yeah, the embedding models and transformers, the name is kind of interchangeable.
Right, could you say, like chatbot? Did you say chatbot or not? Did you say chatbot?
Yeah, I think from what I understand, some of the models can deal with questions as long as it has a base of context from which to generate human text.
I guess my initial question was how the embedding models, how they use they process the data into a vector database.
Yeah, that was the sole use of them in my particular demo, is just to take a stupid joke that no one will laugh at and turn it into. I mean, I laughed. One more in the back.
Compared to other vector databases that are out there, what what's the storage and computation cost? How does OpenSearch compare to those?
It's, I would respond to the question with, the question is, but can you repeat it a little bit louder, just so it's,
Compared to the other type of databases out there, like PG Vector,
sure.
or any other databases, how does the storage and computation cost using OpenSearch compare?
Gotcha. So the question, how does OpenSearch hold up to the other options when you're dealing with creating with the CPU cost and the overall computational necessity of these language models? Specifically, I can't say without a benchmark report right in front of me, but what I can give you some generic advice, and that is the computational need to generate an embedding will always be directly proportional to the number of dimensions that the model, the number of properties or characteristics that the model is going to analyze. So some models are trained just to say, hey, this message has positive sentiment. This user has something good to say about what we've done, so we want to keep this message. Or this one is a complaint and not really, they're trained to do all kinds of things, but the number of things that they look at, the number of things that the models have to consider will always be the multiplier of how much horsepower you're going to need to do that.
PG Vector, the computation cost is low, the storage cost is Snowflake, the storage cost is really low, but the computation cost is really low. So,
Yeah.
yeah, these are things that are way out in the system.
There are some things that that have to be considered there. And one of the things that does happen with different vector database solutions is when we're talking about the output of a language model or the embedding itself, it's a floating point, it's an array of floating point variables. But OpenSearch does what we call vector quantization, where instead of using a full 32-bit floating point value to store those embeddings, you can narrow it down to maybe a 16-bit floating point variable, or there's even binary vectors now, which I'm not an expert on. But you're right, there's different ways to skin that cat. Lots of ways to do it. Okay, I think I've taken up more than enough of my time. I appreciate you having me out here, and if you'd like to have a talk afterwards, I'd love to exchange LinkedIn's and all that stuff. I can make some new super friends for the OpenSearch project. Awesome, thanks everyone.